Hey, so, oh yeah, the stream is beginning for anyone who's watching. Sorry that it's starting just a tiny bit late. Hello, chat. I just got home, so I want to let everyone know that the stream will be starting shortly, but I just need to get a few things in order first. So you'll just have to give me a couple minutes while I get everything together. Maybe I can hopefully things don't get like shut down for copyright, but I'll just put on a trippy math animation, and hopefully that will that should be fine. And I think someone even suggested that I change my the position. Here we go, of where my face is, and I think I figured out how to do it. So yay me! Okay, so we're almost ready to get started here. Just need to plug in my laptop. Okay, great. So I'm now ready. I'm now ready to start. So it looks like I've already got a couple people in the chat. So if people have questions, then that's great. That's a great place to start. If anyone wants to drop a question in the chat. Otherwise, I'm basically just going to start talking about some other stuff that I was thinking of talking about. Unfortunately, I don't have a separate chat window, so I have to go to this weird like infinite fractal video screen to look at my chat box. But I don't see any questions popping up, so perhaps I'll just start talking about things. So probably the first thing I want to go over is the idea of a linear combination. So this question got asked a number of times in so someone asked in the chat if I could explain K-theory in brief. Sort of. Here's the thing. To be perfectly honest, I don't totally understand K-theory. And I mean, there's a mathematical discipline called K-theory. My name starts with a K, so I thought that would be a clever rebranding of my channel. But very roughly, because I don't know the level I'm answering this question at, but very briefly, K-theory is a study of algebra. Well, and there's two different kinds. There's two different brands of K-theory. There's sort of one that's called topological, and there's another one that's called algebraic. So this version, the algebraic K-theory, of course, is better for understanding algebraic type problems, and topological K-theory is more for solving problems about shapes. But both of these actually have a bit of a geometric sort of flavor, and you can think of it as solving geometric problems by using algebra. Now that's very vague and imprecise, but I think I'm going to be doing linear algebra. I'm trying to do some linear algebra problem solving, and so maybe I can make a video another time about a more complete explanation of what K-theory actually is, because I can give you a more detailed explanation. Okay, so let's get to the linear algebra, though. So this week I had a number of people asking me about linear combinations. So there was a number of problems that came up that had this sort of flavor. So it would say A would be the column matrix 1, 2, 0. B would be the column matrix maybe -3, 5, 1. And let's say C would be a column matrix like -1, 0, +1, let's say. And then, so the question would give you these three column matrices, and then it would say something like, which of the following is a linear combination of A, B, and C, right? And then it would give you a couple options. So there, it would be like A, and it would write the column matrix V, and V would be like 7, 2, -4, or something. And then there would be B, and there would be another one, and C, and there's another one. And so then we want to figure out, well, we want to answer this question, right? Well, in order to solve a problem that's asking about linear combinations, well, we need to know what a linear combination is in the first place, right? Like, we can't possibly hope to solve a problem about linear combinations if we don't know what those words mean. So what do we do? Because, right, we're learning about this for the first time, so maybe you don't have the exact formal definition drilled into your head yet. Although the sooner you do that, the better, because this course, you can't get by just memorizing things. You do need to understand them. There are some things you do need to memorize, and definitions are probably the most important thing. So I'm going to go to my textbook, right? Because I'm learning about this. Oh, linear combination. I don't remember what that is. So I go Control F, right? And it actually has my previous search here, right? So you can see at the top of my screen, I started typing linear combination. I didn't even have to finish typing the word. And look, it's already brought up definition 1.32 of the textbook of a linear combination. So let's zoom in here and take a look at what this says. So it says, let x1 up to xn and v be column matrices. And then v is said to be a linear combination of the columns x1 up to xn if there exists scalars. So remember, scalars is just our fancy word for saying real numbers. It's just to, really make clear the difference that, like, oh, we've got matrices, and like we can multiply and add matrices, and we have numbers, and we can like multiply and add numbers, and then sometimes we combine matrices with a number, right? So that's why we have this very particular language to believe it or not, some of you might not believe this, but mathematicians are actually trying to not be confusing. I know it may not always seem like that. We say that V is a linear combination if the columns, V is a linear combination of these column vectors x1 up to xn, if there exists scalars little a up to little a n, such that V is equal to, and then we see each of the column matrices is being multiplied by a number, and we're adding that total thing together. Okay, so what does that look like in our case, right? Well, in this case, our matrices A, B, and C, these are like our column vectors, x1 up to xn, right? And we want to know, is V a linear combination of A, B, and C? Well, if we go to that definition, what does that mean? That would be the same as saying, that would be the same thing as saying that there exists x, y, and z, which are real numbers. So let me rewrite that. So that'd be the same as saying x, y, and z are real numbers, such that little x times a plus little y times b plus little z times c is equal to v. Right? That's just exactly what our definition of V being a linear combination of A, B, and C from our textbook means, right? We can find some numbers that make this up. So just to let you know, what I'm about to explain right now is sort of the long way around. At the end, there's a much quicker way to solve this problem, and I will give you the quicker way to solve it. But the thing we want to do first is we want to figure out why, right? Because I could just tell you, and this probably happened to you a lot in high school or whatnot. I could just tell you how to solve the problem. I could say, look, here's the formula, right? Here's like the Pythagorean theorem or something. And you go, okay, cool. I have no idea why this solves my problem for me, but sure, whatever, I can go and use it. Like I said in this course, it's going to be helpful if you actually understand the concepts here. So let's unpack what this means in our particular situation, right? So I have x times, and then a is 1, 2, 0, plus y times minus 3, 5, 1, plus z times c, so I have minus 1, 0, 1, being equal to v. So this is 7, 2, minus 4. Right? Okay, so just going along, like, mushing things together. So the scalar multiplication of 1 just makes everything, we just simply multiply x here in this first one and multiply all the entries by x. So this becomes x, 2x, and then, of course, x times 0 is still just 0, plus, and then we have minus 3y, 5y, y, plus minus z, 0 times z is 0, and z, or z for my Canadian viewers. Someone pointed that out the other day, that I'm Canadian, but I tend to say z a lot instead of z. But, it rhymes with like c and v, so how could I not? Okay, so then we want to continue, combining these things together, right? I can simplify this equation more by adding these three column matrices together. And what happens when I do that? Well, then I get, I'm going to have a single column matrix. Is the first entry is going to be x minus 3y minus z, 2x plus 5y, well, plus 0, and y plus z. And you know what? Just to make the point I'm about to make a little more clear, I'm going to write the 0 in here, and you'll see why in a moment. Yeah, so if anyone has any questions at any point, yeah, please let me know. Like I said, I can't always Oh, what have I done? I didn't want to do that. Yikes. Anyways, what I was trying to say is please let me know if you have any questions in the chat. Now I've created this extra chat window that I don't know how to get rid of because apparently I'm technologically inept. So I guess that's here now. Cool. Anyways, let's get back to the problem solving. I guess this hello chat is just going to be on screen for the rest of the time, so I'll try and be mindful of that when I'm writing. So okay, what do we have here though, right? So we should also be thinking, I've got a couple tools in my toolkit taking this course so far. Well, what are those tools? What have we learned so far? We've learned about solving linear systems of equations. So probably this question is going to involve solving systems of equations. Well, sure enough, if I look at this, right, this tells me that this first entry of the column has to be equal to this first entry of the column here. So in other words, I have an equation. X minus 3y minus z is equal to 7. And if I look at the second row, I have another equation here. And the third row, I have yet another equation. So what does that mean? Well, right, what am I trying to do? If I zoom out here, take outs and less weird things interrupting us. But now we're back. Okay, so we got 1, 2, 0. We got minus 3, 5, 1. We have minus 1, 0, 1. And then our constant column is 7 to minus 4, right? But now I'm going to show you a little something. So I'm going to zoom out again, and hopefully this isn't too small to read. But if I look, so if I look at A, my column vector A, I'll use green here, it'll stand out a bit more. So it's just the column vector 1, 2, 0. And what's the first column of my matrix? It's 1, 2, 0. I look at B, what's this column vector? It's minus 3, 5, 1. So I look at this, and what's the second column of my matrix? Oh, it's minus 3, 5, 1. And then finally, I look at the column vector C, and you probably guessed it, that's just the third column in my matrix. And then my constant column is just the column matrix in question. So what this means is, right, so I went through this complicated explanation to show you why this solves the problem. But now, you know, because you want to be able to do this quickly if this is on like an exam or something. So in general, we now know that if you have a question that gives you column matrices x1 up to xn, and you want to know is V a linear combination of x1 up to xn, and instead of going through all these steps I did just here, you can literally just set up the augmented matrix whose first column is x1, whose second column is x2, whose third column is x3, dot, 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 and whose final column is xn. And then you put the line, and your constant column will simply be the column matrix in question. And then the answer to is V a linear combination is exactly the same as the answer to does this system of equations have a solution. So if the system has a solution, then V is a linear combination of x1 up to xn. At the same time, if this system of equations does not, so if no solution, then we know for sure that V is not a linear combination. So the quick way to do this then is, so I could have simply said, oh yeah, we just make the matrix whose first column is A, whose second column is B, whose third column is C, and whose constant column is V, and then we just solve that. But you wouldn't have known why, and now you know why. So let's see, is there any questions in the chat right now? No, so I guess I'm just going to keep going. I'm just going to keep, I guess we can may as well solve this system of equations. So I want to get this in reduced row echelon form. So is this in reduced row echelon form? And the answer is no, right? So the way I like to go about doing this is normally I go column by column. So I look at the first column and I ask, well, I only want to have one leading entry, right? We know that fourth condition, that condition that sets reduced row echelon form apart from row echelon form, is that all the entries above and below a leading one are 0. So I look at my first column and I see, okay, I've got some things that are non-zero. So I need to get rid of, well, I only want one thing that's non-zero. And oh, lucky me, I already have something that's equal to 1. So I'm probably going to pick that to be my leading one, which means I want to get rid of the other thing that is not equal to 0. So what could I do? Well, I could take row 2, and I could go, I could transform that into row 2 minus 2 times row 1, because that's going to cancel out that 2. So I get this new matrix. So my first row is staying the same. My final row is staying the same. And my middle row is now going to be, well, I have 2 minus 2 times 1. So that's just 0. I mean, that's why I picked it to be minus 2 in front here. And then now, again, we always have to be careful with the double negative. So here I have minus 2 times negative 3. So I'm actually going to be adding 6, which gives me 11 here. And then here I have 0. And again, I have minus 1. So minus 1 multiplied by minus 2. I'm going to be adding 2 to 0, and that's 2. And then finally, here I have 7. So I'm going to be subtracting 14. So I have negative 12. Okay. So here's my matrix. And what else can I do to it? Now I've got, I've got this first column of zeros. So now I look to this next column and, oh, lucky me, I have a 1 again. So what can I do? Well, I need to get rid of this 11, right? So I'm going to do something to get rid of this 11. I'm going to go row 2. And now because I have a 0 in this first column, I don't need to worry about what's happening in this first column. It's taken care of, right? So that's the important thing. We want to make sure that none of our row operations are taking us backwards and turning things that already are 0 back into non-zero things. So here I'm going to go row 2, and I'm going to subtract 11 times row 3. So that'll give me the following matrix. So I'll have, again, the top row is staying the same. And we have, so this will be, of course, 0 times 11 is 0. 11 minus 11 is going to be 0, as we, I mean, that's the whole reason why we picked this. So 1 times 11, well, it's times minus 11. So we're going to have 2 minus 11. So we're going to get minus 9 over here. And then finally, so again, we have to be careful because we have double negatives. So we'll have minus 4 times minus 11. So we're going to have positive 44 adding to negative 12, which is going to give us a positive 32. And we're a little bit closer, but I still have a non-zero entry above this. So I'm also going to do something to row 1, and I'll go row 1 is going to become row 1 plus 3 times row 3. So we have 1, 0, 0, 0, minus 9, 1, 1, 32, minus 4. And again, right, I don't have to worry about what's happening to the first column because I'm just adding something that has 0 in that first entry. So I've got minus 3 plus 3, so that's 0. I mean, that's, again, exactly why I picked this constant. And then I have 1 times 3, again, is just 3. So minus 1 plus 3 is positive 2. And then finally, negative 4 multiplied by 3 is negative 12. Plus 7 is going to give me minus 5. Okay, so we're getting closer. We're getting closer. We're still not in reduced row echelon form. Yeah, don't be afraid. If you're not finding these questions helpful, tell me in the chat. And I'll work on something that's more relevant to what you need help with. Okay, so we're just about done here. So we have leading 1, zeros above and below it, leading 1, zeros above and below it, and there's this one last entry which is not a leading 1. So how can I possibly do that? Well, I can't use these other rows, but I can scalar multiply. So I can go row 2 and divide by minus 9. So this will be row 2 goes to row 2 multiplied by 1 over 9. And what I'm left with is 1, 0, 2, minus 5, 0, 1, 1, minus 4, 0, 0. This will be 1. And here we'll have 32 divided by negative 9. And unfortunately, that fraction does not simplify. We're just going to have to live with that horrible, horrible fraction in our lives. Okay. But now, okay, so now we have a leading 1, but there's issues. I've got things above and below it. So I still need to do some more row operations. I didn't mean for this problem to take up, the bulk of the time that we have, but here we are. Okay, so I'm going to go to, so row 1, I'm going to transform that to row 1 minus 2 times row 2 in order to get rid of that 2. Again, now, right, notice that the first two entries are both 0 here, so I don't have to worry about what those entries, what impact those entries are having on the other parts of the row. I'm simply going to have here 2 minus 2, which is 0. That's the whole reason I picked this. And then things are going to be a little bit more complicated in our constant column, because now I'm going to have minus 2 multiplied by 32 over negative 9. Still have 32 over negative 9 down here. And then finally 0, 1, 1, minus 4 over here. So you can probably already see what's happening. It looks like we're going to have a solution, and that is going to be unique in this case. But let's keep going. So we can simplify this matrix a little bit, right? So this can be 1, 0, 0, 0, 0, 1, 0, 1, 1. So simplifying these fractions, right? So these negatives are going to cancel out and become a positive. And then I want to, in order to add these fractions, I want to write, I want something to have 9 in the denominator here. So if I divide by 9 and multiply by 9, it has the overall effect of multiplying by 1, but it changes things. So we have a 9 in the denominator. So I'm going to have 5 times 9 is, well, it's negative 5 times 9. So I'm going to have minus 45 plus 2 times 32, which is 64. And this is all happening over 9. And the final result is 19. I believe. Yeah, believe it or not, I'm a mathematician and my mental arithmetic is terrible. So yeah, feel free to correct me in the comments if you think I'm making a mistake, a small like calculational error, because I probably am. Okay, so then the final thing that we need to do then is well, again, we're looking at this final leading entry. I need everything above and below it to be equal to 0. And so this last one I can achieve by simply going row 3 minus, row 3 gets sent to row 3 minus row 2. And finally, I'll be left with this matrix, 0, 1, 0, where my constants are 19 over 9, 32 over 9, and this will be minus 4 minus 32 over, so it'd be 32 over negative 9, but since we're subtracting, the double negatives become a positive. And I'm almost at the end here. So I get 19 over 9, 0, 0, 1, 32 over 9, 0, 1, 0. And again, I want to write this as something that has 9 in the denominator. So I multiply by 9 divided by 9, which is just multiplying by 1, which isn't really changing anything. Then 4 times 9, of course. So here I have minus 36 plus 32 is going to give me negative 4 over 9. Okay, so is this matrix, ask yourself, is this matrix in reduced row echelon form? It might be tempting to say yes, but it's not actually. So in order to get this to reduced row echelon form, remember our leading entries need to be moving to the right as we move down, right? Or as it's phrased in the textbook, right? Every leading entry needs to be to the right of the leading entry above it. And if we look at the leading entry here, well, there's a leading entry above it, but it is the leading entry in the third row is actually to the left of the one above it. So we're not supposed to have that. So in order to get this in a reduced row echelon form, we should also apply the transformation swapping row 2 with row 3. But even without doing that, chat, I don't know if you heard that. I don't know why the robot voice is saying that I've joined with my email. I think I'm just going to have to switch over to a new streaming platform, probably. And I hope I hope I caught that screen going black right away. I hope people let me know if that happens. So I'm not spending the entire time with a screen that's gone black. Okay, so these, right, this is the question that we originally asked, right? Is V a linear combination of these column matrices A, B, and C? And then remember what we did is we turned this question into a question about solving linear solving a linear system of equations, right? And we got this from asking the question, well, does there exist an XYZ that makes this equation true? And then we solved that linear system of equations and we found, yeah, well, there is an XYZ that makes that linear system of equations true. And what that means is that that exact same X, Y, and Z is going to work to make V a linear combination of A, B, and C. So you can check this for yourself. I'm not going to do it on the stream because this is just, practice doing some calculation. And I could probably better use that time explaining other concepts. But if you literally plug these numbers in, you should find that this equation works out to be true. So this is a good, a good exercise just in practicing computations with matrices. / you can check to make sure I've done my math right, and bug me about it on the next stream or in the comment sections if you find an error here. So yeah, what you literally need to do is just multiply in each of these constants and add these 3 matrices together, and it should work out to this. Here's a little life hack for you, though, because this computation looks like it sucks with all these fractions. You can actually, since all of these numbers are being divided by 5, you can actually factor that out and just do the calculations, factor that out in front, do the calculations with all of these constants here, and only after you've done all the addition and combined these matrices and added them together, then you can multiply the 1/9 back instead and check that it's equal to 7, 4, minus 2. Okay, so does anyone have any other questions, maybe things you've been working on? Not homework problems, obviously, but maybe, examples from the textbook, things from class that didn't quite make sense the first time around. Because if not, I guess we'll move on to some other things. So an interesting question. Someone had asked me, well, why don't we? Okay, let's focus on practical. Let's problem solving ones. So here's a question where you might get something like there is a jar with, let's say 17 coins made out of nickels. Don't know how to spell that word. Nickels, dimes, and quarters, let's say. Let's just do the three, right? We've got nickels, dimes, and quarters. And the total value is equal to, say, $1.35. And we want to know what are all the possible combinations of coins. Or a better question is, well, I guess this is the same one. Is how many ways or how many combinations of coins satisfy this? I.e., what are the possible numbers of nickels, dimes, and quarters? Okay, so this seems like, wow, I've totally shifted gears. Here I was talking about linear combinations of column matrices, and now I'm talking about coins in a jar. But if you're seeing a problem like this and you're in, say, your number theory course, you have to remember, well, we're not just throwing random problems at you that are impossible to solve. We're giving people, we're giving you the tools to try and solve these kinds of problems. So the only tool you have right now is solving systems of linear equations. So somehow we have to think, well, how can I take this problem and turn it into a linear system of equations where I can then solve it? Well, what are we trying to solve, right? We want to know how many nickels, dimes, and quarters there could possibly exist. What combinations of those could possibly exist? So a good choice for our variables could literally be these three letters, N, D, and Q, right? Where N is going to be the number of nickels, the dimes, or the D is going to be number of dimes, and the Q is going to be the number of quarters, right? And we have, right, we need to come up with some system of equations that relate these variables. Well, we have two pieces of information, right? We know that there's a total of 17 coins, no matter what the numbers happen to be. And we know that that value adds up to $1.35. So to say that there's a total of 17 coins means that N plus D plus Q has to be equal to 17, right? The jar is made up of coins, which are all nickels, dimes, or quarters. And so if I add up the amounts of each of those individual types, that's got to give me the total number of coins in the jar. For the second equation, I know that the total value is 135, or is $1.35. But writing this out in cents, I have, well, for each nickel, well, each nickel is worth 5 cents. So the total contribution from the nickels I have in this jar is going to be however many nickels I have multiplied by 5, because each of them are worth 5 cents. So same thing with the dimes, right? Each dime I have in that jar is going to contribute 10 cents, and each quarter is going to contribute 25 cents, up to a total of 135 cents, right? That's exactly what $1.35 is. So now I have my system of equations, right? I've taken all the information I have about the system, because I really know two things: that there's 17 coins, so I have an equation describing that, and that the total dollar amount is $1.35, and I have an equation describing that. So now I can go and try and solve this system of equations. So that's what I'm going to do. So the first thing to do, of course, is to set up our augmented matrix. So that's going to look like 1, 1, 1, 17, 5, 10, 25, 135. Okay, so the very first thing we can do is, well, we've already got a leading 1. So it would be pretty tempting to simply just use that to knock this thing out. But there's one thing, and I mean, you don't have to do this, right? But big numbers are terrible, right? They're harder to work with. So it would be nice if we could get rid of big numbers. And something to keep your eye on in problems like this, or in general, is when you can divide a row by something, right? Because if you can divide a large number, you're cutting down its size, you're making it easier to work with. And so you got to keep your eyes peeled. And this will just come with experience solving lots and lots of problems. But notice that 5, 10, 25, and 135, these are all divisible by 5, right? Anything that ends in a 0 or a 5, you can divide it by 5. So the first row operation I'm actually going to do is I'm going to go row 2, and I'm going to divide it by 5, which is the same thing as multiplying it by 1 over 5. So my top row is staying the same. And my bottom row becomes, well, 5 divided by 5 is 1. 10 divided by 5 is 2. 25 divided by 5 is 5. Now, 135, right? So I would, I'm sure some of you out there can just solve this instantly. But I would like to think of it, I like to think about it as breaking this up into 135, right? So now these are easier ones to solve, right? So if you know your multiplication by 5 table, or you just want to count on your fingers, what have you, 35 is just 7 times 5, right? And 100 is 20 times 5, right? So when we divide out these 5s, what we're left with is 20 plus 7, and so what we have here is actually 27. Okay. So now, right, so that is one little extra step in between, but now don't we have such a nice, way nicer system of equations, right? 135 is big, gross 3-digit number, and now we've cut it down to something a lot nicer, right? 27. Okay, so now, because I have 2 leading 1s, right? So the question is, well, which one do I make the 0? It doesn't really matter. But for me personally, I have larger numbers here again, right? All larger numbers in the bottom row. And if I subtracted the first row away from the second row, I'm going to make those numbers even smaller yet. So I'm just going to be making my life easier. Whereas if I did it the other way, I would end up with some negative numbers, and that's just like slightly more complicated to work with. So I go row 2. And I'm going to transform this into row 2 minus row 1. Let me just check that no terrible things have happened to my stream for the umpteenth time today. And so I'm going to have 1, 1, 1 in the top in 17. And then the bottom is 1 minus 1 is 0. 2 minus 1 is 1. 5 minus 1 is 4. And 27 minus 17 is 10. Okay. So that takes care of my first row. Right, I've got a leading 1. I've got zeros above and below it. So my next row, I have this this other leading 1, but I have something that is non-zero above it, so I need to get rid of that. But now I have the luxury, since I have 0 in my first entry, I don't need to worry about how that first column is going to get affected. So I can just go row 1 and transform that into row 1 minus row 2. And so now I'm going to be left with, well, 1 minus 0 is still just 1. 1 minus 1 is 0. 1 minus 4 is negative 3. And 17 minus 10 is 7. And then, of course, I haven't changed anything in the bottom row. And now, is this matrix in reduced row echelon form? Think about it for a second. It actually is. This matrix actually is in reduced row echelon form. Why? Well, if we go through our checklist, right, all the rows of zeros are at, well, there are no rows of zeros. So they automatically satisfy whatever condition our rows of zeros are supposed to satisfy. I have all my leading entries are equal to 1. And each leading entry is to the right of the leading entry above it. And then finally, all the entries above and below all of the leading ones are equal to 0. So this is in reduced row echelon form. So we can't possibly make this any simpler of a problem to solve. And now notice I have these two equations, and I have a third variable which doesn't appear. So this could be a free variable, right? So normally we would write something like let q be equal to t for some t a real number. But here's the issue, right? Remember the problem that we're trying to solve, right? N, D, and Q, these are supposed to represent amounts of physical quantities, right? So these are only going to be whole numbers, right? N, D, and Q, these are only going to be numbers like 0, 1, 2, 3, ... right? These can only be these numbers. They can't be negative. They can't be fractions. It can't be a weird thing like pi. So we normally denote the set with this sort of fancy n, which we call the natural numbers. Right? So we know a couple things then, right? We know, for example, that these have to be natural numbers, and namely that n, d, and q all have to be greater than or equal to 0. Right? So not only do we have this system of equations that has to be satisfied, but we know we have a couple extra equations here, right? We have the equation that n has to be greater than or equal to 0, that d has to be greater than or equal to 0, and that q has to be greater than or equal to 0. And so we can combine this to get more information about our system. So here, we're actually going to let q be equal to t for some t being a natural number, right? Namely, it satisfies this equation that it's greater than 0. Okay, let's plug that into our other equations and see what that system says. So the system tells us that n minus 3 times q, so minus 3 times t, is equal to 7. And it's telling me that d plus 4 times q is equal to 10. So if we look at this first equation, and I should write my q as a t. So if I want to combine, my first equation has information about n, and this other equation has information about n. So I want to combine these two pieces of information. And well, if I add 3t to both sides of this equation, I know that n is equal to 7 plus 3t. And I know this has to be greater than or equal to 0. Well, this equation doesn't actually tell me too much, right? Because I know that t is greater than or equal to 0. And if I'm just adding more things to it, well, yeah, of course, I'm going to get something that's greater than or equal to 0. So not much extra information there. But if I look at the second equation and I try and do the same thing, I move this over. Now I have that d is equal to 10 minus 4t. And this has to be greater than or equal to 0. And so did my... so what happens here, I can sort of forget about the d, right? Because I know this equation has to hold. This has to be greater than or equal to 0. So if I add 4t to both sides, I get that 4t has to be less than or equal to 10. And in other words, if I divide both sides by 4, t has to be less than or equal to 10 divided by 4, which is the same thing as 5 divided by 2. But of course, 5 divided by 2 in decimal form is 2.5, right? And since I know that t has to be a whole number, really this tells me that t has to be, well, greater than or equal to 0, as we know, but it also has to be less than or equal to 2. So in conclusion, there are 3, and to just drive the point home, I should say there are exactly 3 solutions. Right? Because, why is that the case? Because t was our free variable, and then the other variables were completely determined by whatever t happened to be. And in this case, we know that there's only 3 choices for t, right? It's got to be an integer. It's got to be at least 0, and it can't be any bigger than 2. So t can be equal to 0, 1, or 2. In other words, to write this out very explicitly, if, for example, t were equal to 0, then our number of nickels would be equal to 7. Our number of dimes would be equal to 10, and our number of quarters would be 0. So this is the t equals 0 solution. For the t equals 1 solution, just plugging these into our formulas, n in this case would be equal to 10, our number of nickels. Our number of dimes would be equal to, plugging t equals 1. In this case, our number of dimes would be equal to 6, and our number of quarters would be equal to 1. And then finally, the t equals 2 situation, we would have the number of nickels being equal to 13, the number of dimes being equal to 2, and the number of quarters being equal to 2. So there are exactly 3 possibilities of what amounts we could possibly have for nickels, dimes, and quarters, such that we have a total of 17 coins, and that total adds up to $1.35. Okay, so I think that's basically going to do it for the stream this week. So thanks everyone for watching. If you have questions, yeah, don't be afraid to drop them in the chat. Don't be afraid to come out and ask. Have some questions prepared for next week's stream. I will try to be on time. just like I wasn't this time. But I'm gonna try and be on time for next week's stream, and hopefully you guys will have questions for me about linear algebra, and then I can help work through your problems. But again, like always, if you don't, not a big deal. I will be coming up with my own problems too. So okay. I should also probably change that so my Discord messages aren't randomly popping up and things like that. So thanks so much, and I hope everyone has a fantastic week.